This is Mu Yang from CMU. In this video, we introduce our work, Efficient Spatially Sparse Inference for Conditional GANs and Diffusion Models. Generative models have enabled many image synthesis and editing applications. For example, GAN can convert semantic maps to photorealistic images. And SD-Edit could edit real images with strokes. However, recent models often synthesize the entire image, even for minor edits. For example, DDIM requires 249 Gmax computation for 50 steps given a user input. Then the user adds a new building, which occupies about 9% pixels. Unfortunately, vanilla DDIM costs another 249 Gmax per step to resynthesize the entire image. This wastes too much computation. In fact, the feature maps stay almost the same for the unedited regions. Motivated by this, we propose spatially sparse inference. Our key idea is that we cache the feature maps of the previous edits. For the new edits, we reuse the cached feature maps and only apply convolutions to the newly edited regions. It reduces the computation by 5 times in this example. We further proposed sparse incremental generative engine, SIGE, to translate the computation reduction to measured speedup. SIGE uses a tiling-based sparse convolution algorithm. We wrap each convolution into SIGE-conv. AL is the input activation to the else convolution, FL, and the corresponding output is FLAL. The features of the original image have been computed. When the editing is finished, we compute a difference mask to locate the edited regions. We downsample the mask to different resolutions. For each resolution, we divide mask into small blocks and reduce it to active indices, which index the edited blocks. After we get the edited input activation, we use the active indices to gather the edited blocks along the batch dimension. We feed these blocks into FL, and then scatter the output blocks into the original output activations. In this way, we compute the edited output activation, and eventually get the final output. You could also refer to the previous work SBNet for the tiling-based sparse convolution. However, this algorithm fails to deliver a prominent hardware speedup due to the overheads in gather and scatter. Therefore, SIGE further adopts several optimizations to better support image editing. Here, we show the pipeline of a convolution block used in DDIM. Recent generative models often use instance normalization or group normalization, which compute statistics on the fly during inference and incur significant overheads. As mentioned before, the edited activations and the original activations are very similar. This allows us to cache and reuse the statistics of the original activations. We can replace normalizations with scale plus shift. Additionally, we move gather to the front of scale plus shift and further fuse these operations together. In this way, we can apply the elemental-wise operations only to the edited regions and perform in-place computation, which reduces the number of kernel cores and memory overheads. Please refer to our paper for more details on kernel fusion. Here, we show our results. These are the input images and user edits. And here are the outputs from vanilla DDIM. Our method achieves similar results while reducing the computation by 4 to 7 times. In the 1.2% added example, our engine achieves 3 times speedup on 3090 and 6.6 times speedup on Apple M1 Pro CPU. Our method reduces 18 times computation for GAN. It is also complementary to existing model compression methods. When used together with GAN compression, it reduces 50 times computation. Correspondingly, Sage achieves 4 times speedup on 3090 and 14 times speedup on Apple M1 Pro CPU. With GAN compression, it further achieves 38 times speedup on Apple M1 Pro CPU. Our code and the benchmark are publicly available. Thank you.